now we want to add these roles for types. So you see, we have a problem that sometimes it should be allowed, sometimes it should not be allowed. So the easy thing is to say, well, it is never allowed. And type system is generally, it is doing things like that. Say, well, this is not a good thing. Let's not allow it. So let's disallow it, and that's it. So that's one answer from some type systems. Good type systems should think about it differently. Say, well, if we may come out with a case when it should be allowed, let's allow it. If it's a bad idea, well, let's disallow it. So we can think about it. Whether to put those roles. We have values, we have types. What else do we have? We have kinds, which comes from system of omega. And those kinds, that's exactly the place for putting type roles in there. So what they are doing? Let's say, okay, before that we had only one kind, this star here. And also we had these arrows for type level functions, like in maybe has kind star to star. All right. Then we have two roles. This will be nominal role, and this will be representational role. And now we have new sort of kinds which are parameterized with this role. So this will be type which is nominally with nominal role, and this will be type with representational role. All right. And now we have to put these kinds into real expressions. We know for maybe that it has non-parametric occurrence, and that means that its kind will be this one. So remember, when it's parametric, you are free to do whatever you like. So you can do lifting for representational equality. So we say, well, it's parametric, then it will be this one. If it's not parametric, like in inspect, use this one. So you need an algorithm which decides whether this occurrence is parametric or not, and then it assigns the right kind to this type. So remember, we have no such things in Haskell source code. All this stuff is actually inferred using type checking. Sometimes it's this one, sometimes it's this one. So this nominal will be. And now this is a new type for the axiom. And it says that you will be able to use this coercion. This will be coercion in representational sense. So this is specified right here. And then it's very simple. So remember our rule. So if you have representational equality and if you have parametric occurrence, then you are free to do this lifting. Otherwise, you can do this lifting only in the case of nominal equality. So all these words, they are very difficult to say, they're very difficult to understand, unless we look at the typing rule. This is quite difficult typing rule, but as usual, it gives us an algorithm for solving problems. So this rule allows us to do everything with maybes, and it doesn't allow us to do everything with inspect. So every difference between them is encoded with this rule. So let's look at it. So we have these two roles, N and R, nominal and representational. So this, we defined this before in the previous slide. And now let's see how we can use this typing rule. So remember, we have two things. we have int and h, two types. They are representationally recursable to each other, or representationally equal. And we want to decide whether it is possible to write maybe h equal to maybe int, or inspect h equal to inspect int. So that's the question. So if we can type check something, then that's all right. So according to this rule, we should be able to type check maybe int equal to maybe int, and we should not be able to type check inspect h equal to inspect int. So we should see it right there. For example, if we have maybe, let's see. So phi1 and phi2, phi1 and phi2 here, this will be maybe or inspect. You see, it's type application, and left part is either maybe or inspect. So phi1, phi2 will be either maybe or inspect, and these psi1 and psi2, they will be int and h. Now, what we have for maybes? Maybe and maybe. So let's find out what we have here and what we have here. So what about this one, R2? What should be it in the case of maybes? R2 is what? Is it N or R? It's R, because it's our maybe. Because there was parametric occurrence there, so it's R. So this R2 is R. All right, so this will be star again. What about this R1? Can we see it here? In fact, we don't need it right now, but remember that we'll need to fix it sometime when analyzing this rule. Okay, but R2 is R. All right. Then, what about these types? Int and h. What about this? R2 we know is actually R. And what about R1? I think I'm just is just a second. When I'm talking about this rule, I'm in trouble. I'm trying to get it. All right. So the idea is, can we find R1 and R2 so that this typing rule is satisfied? So that's the right question that we should ask ourselves. So we know that R2 is R. All right. And what can be this minimum? It can be either R or N. So if R1 is nominal, then can we type check this? If this R1 is nominal, can this be type checked? Look, if R1 is nominal, then what about this minimum? And think about this equation. If R1 is nominal, and what about this minimum? It's also nominal, and then we can type check it when it's nominal again. So with maybe it is possible to do that for nominal R1 and representational R2. So we can do that without any problem. So for maybe, we just come up with special R1. If R1 is R, is it possible to type check this with maybe? If R1 is R, then this minimum will be, it will be R. And we can type check it because R1 is R, but we'll get something different here, but it still will be type checked. So with both R1. So we can type check it in every case. And that means that for maybe, we can lift it for in any context, independently. Is it nominal? Is it representational? We're on the safe side with maybe. We can do that. But if this phi1 and phi2 is inspect, then what does it mean? Then here R2 is, what is it now? It should be n, so it will be nominal because we have this non-parametric occurrence here. And now we have this psi1 and psi2. And what about this minimum? What should it should be here? You know, you can see this right now. So this minimum should be R. And is it possible to get minimum of R in the case, so minimum equal to R when R2 is nominal? Like here, is it possible to get minimum of R? No, it's not possible. And that means that this rule restricts us, so we cannot do such thing for inspect. Because, well, technically, this minimum cannot be R in the presence of nominal equality. That's it. So it's so simple. Just one inequality here. So sometimes we can type check, like for maybe, and sometimes we cannot type check, like for inspect. So that was a solution, and this solution introduced system FC2. So it was coercion with roles. And they implemented this coercion for several years. It takes to implement it correctly. And I think they finished this implementation in 2013, finally. I think it's all right not to understand this example, by the way. I understand it not a very good way too. But I just believe to typing rule. So I see technically this is restricted, this is okay. And then it's just fine. All right, so this is system FC2. It works, this paper, it has definition of roles, and it was a component of a kind, like star / nominal or representational equality. So there were theorems about progress and preservation, so this type system is still good. By the way, remember, we've proved progress and preservation for system FC2. So it was very good type system. But unfortunately, it was not so good in the presence of other advanced features of Haskell language. So again, we are not guaranteed that this new, super new paper-proofed extension will work in other situations. Because when you introduce many features, they can interact with each other in very different ways. So they updated translation rules for GADTs, for type families and other stuff. And they also introduced some implementation of system FC. So they decided that they just removed several operations over the coercions and stuff like that. So simplifying means that they just remove something which is unnecessary. So there were several things there. Okay, we have not much time. All right. So the next step for us is another important extension of GHC Core, something which is called FC Pro. FC Pro. This is how we pronounce that. FC Pro. This extension was modified with the following example. This is textbook implementation for vectors or some data type with fixed length, and this length should be checked at the moment of type checking, so before actual before runtime. And in GADTs, we just use types for controlling things. So we have a constructor of empty vector here, and this component of a type will specify that this will be vector of size 0. And then when we add some new element to the vector, we just compute successor to this type, and then we have different size. We're using these two types, 0 and successor to n, without any representation. We don't need that. So they exist only in the time of type checking. So, but if you are type checked, then you are on the safe side, as usual. So this is a very old example. There are 10 years to this example since the introduction of generalized algebraic data types. But what do we know about the 0, suc, and vector? They have these kinds. And the problem is that these kinds, they are not controlled. So we can do very strange things as suc to bool, or vector of 0 int, and something like that. So we have very good control for types of our values, but we have no controls for types of our types. So just only one kind of star, and we can put whatever we like into these slots. So that's not a good idea. So you can think about it like this. So you have strongly typed language, Haskell, but you are doing type level computations like in dynamic language, like in Python, for example, with no control from the type system. Isn't it embarrassing? And many people thought that, well, it is embarrassing, in fact. So it's not that good. We need more control over type level computations. Otherwise, it's not a very good thing. So the next step is introducing such control. And it was described in the paper giving Haskell a promotion. So this promotion, and that's why it's called System FC Pro. So the idea is as follows. So we can define such data type. It's usual algebraic data types for natural numbers, 0 and successor to a number. And then we want to have an ability to specify that second argument of this type level function vector should be natural. So see, here natural is a type, but here natural, it's not a type. It's a kind. So we want to promote data type not into kind not. And then we say, well, we should use natural numbers, natural type in this position instead of a kind. And now everything is controlled. So you cannot put bool into there. You cannot put int here. Just only 0 or successor to any other number. So there are two extensions which implements this, data kinds and polykinds. The implementation started in GHC 7.2, I think. Then in GHC 7.4, they introduced data. So once it was one extension, polykinds, and then they re-implemented a little bit, and in 7.4 they had polykinds and data kinds, and then finished this implementation in 7.6. So it's about 2012, 2013. So these times. So two extensions. Now every such type can become a kind, and every such data constructor becomes types right now. And that's why they will be type checked. So if 0 is a type, then you can use it in type annotation. Again, suc is a type, then you can use it in this type annotation. So everything is good here. So that's Haskell, as we can use it right now in the Haskell without any problems. And we can use even more interesting things. So we can define type family or type level function plus, and we can compute it as follows. Again, so if you know this type family extension, which is more than 10 years old, then you can do these things. But now you can control your arguments. So you cannot put plus for some strange types. You have to put only types of this kind not. So everything is controlled so that we can implement other functions. For example, this is function for concatenation for two vectors, and it's like almost Idris or other dependently typed language, and we can do that in Haskell for many years already, and everything is type checked thanks to these extensions. There was also part of this work for implementing equality for types. When they have different types, you have to specify when they are equivalent, when they are not equivalent. So such data type was introduced. So there is only one proof for equivalence of two types, is reflexivity. So one type is equivalent to the same type, and to different types they are not equal to each other. Then polykinds allows us to implement the same equality, type equality, in other settings. So maybe doesn't have this star kind. It has star to star kind. So in this situation, then you will need another type. So polykinds extension just allows you to do these things like that. But remember, we are not interested here in Haskell language itself. Our question is, our problem in this workshop or lecture, our problem is how to translate all this stuff into GHC Core. So I assume that everybody knows all this stuff because it's source Haskell. So it's not about what we are interested in here. So from this paper, we've introduced new abstraction. So we had lambda for types, and now we had third sort of lambda for kinds. So you can read it like a little bit bigger lambda. Now we had small lambda for values, we have big lambda for types, and we have a little bit bigger lambda for kinds. So three sorts of abstraction and three sorts of application. So the system GHC Core becomes more and more difficult. You have three sorts of abstraction, three sorts of application, and in such situation, you need to classify kinds. If you have more than one kind, then you have to classify it. So you have to introduce something like type of a kind. And then you will have to invent something, and then you will have to classify these types of kinds to add another level of classification. And you can follow this path forever, technically. And they've introduced this primitive classification of box. So box is like we had kind star before for every type, and now we have this sort box for classifying kinds. And I remember those times in about 5 years ago when Haskellers talked to each other and asked them, what do you know about boxes? And it was really hot topic that time because nobody understood it. What is it? So we were used to kinds already, and some of us were used to roles already, this representational nominal, but only few of us read this paper and know about boxes. And it was really difficult because, several levels of classification is hard. It's very hard to put in human mind. This paper also introduced another kind, except for stars. This kind was used for constraints, for type classes, actually. I will follow very quickly. I will not explain all this stuff here. So we had to introduce kind polymorphism here. And this type promoted means like when you had data constructed is promoted to type, you have something at the type level new here. So everything is extended. You have to add more and more notions to this GHC core. So still you have some extension, but there were many limitations, and there were no promotions for complex types. There were no promotion for functions. It was very difficult to promote something with polymorphic kinds. So many limitations. So this paper, it was good for examples like vector and other simple stuff. But it was very difficult to use it in practice because it was really very difficult extension. Nevertheless, this is an achievement that we've got using this paper, giving Haskell a promotion. This kind system was enriched in a very difficult way. We've got this new system FC Pro. And of course, we've proved they were proved like progress, preservation, every type theoretic property was proved. Type inference algorithm was changed because we had to control these new kinds and all stuff like that. The next paper here was very important to us today, and it was a paper of 2013. And there was one crucial decision that was made there. We've said, well, we don't want to think much about all those kinds. Let's say that types and kinds are the same. So we don't want to think about classifying kinds with all those boxes and everything we could come up after that. We just say, well, types and kinds are the same thing. And this was done for GHC 8.0, and we had this new property here, and extension. It was implemented in the form of extension type in type. Richard Eisenberg did that for GHC, and this was first step to the dependent types. So this paper actually introduced equality for kinds, and it allows kinds to depend on types. Every type theoretic property was proved. Some limitations were weakened, limitations for system FC Pro. But in that 8.0 GHC, this type and type extension was, well, I can say it was unusable. There were too many problems with using it. Actually, it subsumed somehow polykinds and data kinds, but we still have in the recent versions of GHC, we have all of them. So we can enable type and type, or we can disable it. We can enable polykinds and we can disable it. And the difference between them, well, although type and type includes all this stuff from other extensions, but we still can't count on it. So because we don't understand everything about this type and type still. So this I was reading a documentation for GHC 8.4, which was released in March, I think, March this year. And they still write there that, well, we don't understand type and type. What is it? So we can't trust it yet. So polykinds is all right, data kinds is all right, but here we still have problems, and it's about 4 years for this extension. So we don't understand it actually, and we can't trust it. So before that, 2012, we had GHC Core as follows. So we still use, with all this FC Pro, FC2, we still use the name system FC, but with all this stuff. So this is very close what we had in the beginning this morning. So you can see here only one sort of lambda abstraction, but we'll use it for types, for kinds, and for values. You can also see here one abstraction, or one application, and it will be used for values, types, kinds, for everything. You can also see coercions here, and these cast operators that we've discussed here. Here you can see these ticks in Greek too. And these are very different types. You see types, kinds, and whatever. We can use the same system here. Function types, type constructors, type application, universal quantification. You can see all this stuff here. And that time we had GHC Core with many typing rules, with many kinding rules, with coercions, operators over coercions. We had roles. We had core linting. Linting is like a set of algorithms which allows us to make sure that everything is all right with our GHC Core. But then there were two PhD theses which are very close to each other, and both of them discussed the same topic. But look at the types of these theses. They're very close to each other. You can see word dependent types there. You can see word Haskell in both of them. There's 3-year period between these two dissertations. And one other thing, when you write two dissertations on the same topic, with almost the same title, what does it mean for the first one? So, yeah, so, well, basically that means that you have some problems with the first one. Mm-hmm. So it's incorrect, maybe. So there are some problems. And then you write another PhD thesis on the same topic, and you want to correct this problem. Unfortunately, this second thesis, it was wrong too.
Oh, God. This is really hard.
Yes, it is. But yeah, it's not a bad thing. You have more doctors thanks to this process. It's very convenient for scientists,
Yes.
There is one problem. Well, the problem was when you prove properties about your system. If you do that on paper, then you cannot trust these proofs, because these proof papers, they can have errors, and you cannot see them, and your advisor cannot see them, and your PhD committee cannot see them, but still you have those errors in those proofs. So they were very close to each other. This is the structure for both of them. So both papers, they defined outer language, like new language. It's some extension of Haskell. In the first thesis it was inch, and here it was dependent Haskell. So you see it's rather, well, it's a good name, but it was just a name without actual implementation. Then you have to define type inference in this outer language. Then you come up with an inner language, like GHC Core for those languages. So these are their names. Language of evidence in Gandry thesis, and PyCo in Eisenberg thesis. Then you have to provide algorithm for translating outer language into inner one. Then both theses, they give you lots of examples on how to program with dependent types. So, of course, it was impossible to program because there was no compiler. But still, those examples, they're very good. They are very interesting examples how to do that, how to write very good programs using dependent types. And then they provide some implementation details. So they had some playgrounds for these types, for those languages, but as usual with PhD, it's impossible to use them after defense. It's quite regular thing. That's why we need GHC to implement everything in GHC, because then it will work. Otherwise, you cannot trust it. It's just some student program. And then in 2017, there was a paper in ICFP, International Conference for Functional Programming, with almost the same name as those theses. So again, both theses were wrong. So you cannot rely on them when implementing actual compiler, actual dependent Haskell. So they've come up with another approach. They say, well, if it's so difficult to prove things on paper, why not prove them in something more formal? So why not prove them in Coq, language for proving things in type theory, on programming language theory? And nowadays, it's quite a common practice for type theory research. So if you submit a paper without formal proof in Coq or Isabelle or other proof system, then nobody believes you. So even if you provide this proof, then nobody believes you, because they can say, well, your specification is not very good or something like that. But still, if you have no formal proof, then absolutely no believe you. So they try to deal with all those problems we had before. And this paper is actually, well, we think, so community thinks right now that it's a good step. So we believe that in 2 or 3 years, this will be implemented in GHC, and we will have really dependent Haskell. So Haskell with dependent types. All right. What is the goal of this paper? The goal is to design such extension for Haskell which has no difference between types and terms. Remember those previous steps when they removed difference between types and kinds. So we want to go even further. We should say that there is no difference between terms, values, types, kinds. All this stuff is just the same thing. That's the goal. And that means, by the way, we want to simplify our core. Because now we have this distinction between values and types. And we want to simplify it, just to use just one thing for them. One abstraction, one application for all of them. So that's a goal. And then we also want to do this thing. So we want to share semantics between evaluation at runtime and compile time. Because in dependent types, when you have values, when you have types, some of the computation is done at runtime, some of computation is done at compile time, and you want to do it in the same way. You don't have to provide different algorithms for these computations. So technically, what they did in those papers, yeah, it's 2017 again. It was presented in September. So they provided system DC. So it's dependent types with coercions, with an idea to make it compatible with system FC, which we were talking about today. Then they also wanted to provide system D implicitly typed version. So remember that GHC Core is explicitly typed. So they wanted to look how things are going on when you have implicit thing. So is it possible to reconstruct types in this type system? So that's why they need that. So they want to talk about erasability, because here I was talking about erasability several times today. So if you have types, then you can erase them before evaluation. If you have types which depends on terms, sometimes you want to erase terms, sometimes you don't want to erase them because, well, you have nothing to compute with on runtime. So it's a difficult question here. So in order to work on this question, you have to come up with some formal system and prove theorems about that, something like that. And then the system D is also able to give you some ideas on how to do type inference in this outer dependent Haskell. And then they say that they formalize and prove it in Coq with SS-reflect and extension in Coq. Finally, they published their paper in about January online. So it was January 2017. So before the conference, so it was like draft paper. But they did not show their Coq code for 7 months. And everyone was so excited with it, but they did not show it. So many people suspected that there are some problems in their proofs. So it was very funny. But then they showed it, and actually there were some problems, really. So what we have in this extended type system with dependent types. Remember this example. So we don't need some data promotion here. We just have one data type not for natural numbers, and then we can use it in the type of vector. So vector depends on type of elements, size of vector, and that's our resulting type. This keyword type is also type and type extension, actually. So it is possible to use that right now. So this example is just the same as in the languages with dependent types. So if you know Idris, it just looks the same. No difference with Haskell. So we want to do that. And
that doesn't exist. That's not right now. You can't write that. Or you can
No. In current Haskell, you can't do that.
You can't.
Yeah.
Or can't.
I think you can't. You can't do that. You can do that. Yeah.
Okay, got you.
So this is how we should translate it into system FC. So with all types clearly specified. Do you see these coercions here? So we use these coercions for values, not for types. So n is coercible to 0, like this one. Again, it's like usual algebraic data type, because we have the same type here, vector of a and n, vector of a and n. So two constructors, they are typed with the same type here, thanks to coercions. All right, and this is how function over vectors is looked like now. So you can see this new type here with several components which are universally quantified, and we use them for erasable components here. So erasable means something that you can erase before evaluation. Size of vector can be erased. It's part of a type, and if a type checks, then you know already that everything will be right with your size of a vector. So you can freely erase it. You don't have to keep this size of vector during your computation. So that's why we use this for all for this component. So it's a term component of a type, but we can erase it. And also, yes?
Is that a choice that you're making when you write zip? So that you might write some other function where the size of the vector isn't erasable?
Yes. 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 Yeah, and compiler should be able to decide that, of course. So it can erase it right here in this example. So look that we don't have to provide other clauses for zip function, because it's impossible to have nil for first argument and something like that for second argument, because they should have the same type, and we can see it here. This should be the same type here. So your type checker should decide that, well, really you don't need those two additional clauses. So if you have lists, then you have to specify all four clauses. Nil and nil, nil and not nil and nil, and two not nils. Here you don't have to do that. And this is this function in systemdc. Well, I will be very quick to finish this. So I don't expect that you understand something from the last slides of this workshop.
Well,
That's fine.
question.
Yes.
How far is right now using that in GHC the new so it's like
Well,
actually it's
not far.
not far, okay.
Very, very not far, I should say. Well, usually it takes 2 to 4 years to implement stuff like that. This is rather difficult extension, and it's all right to have 5 to 6 years. So paper 2017, so we can expect that in 2022. Now it's June 3. So it will take some time, yes. Right.
How good will it be at figuring out proof erasure? Or do I have it to specify it explicitly? Or currently, for example, the figure you have to pay often a high price for all the witness that you provide, so kind of if you run them overhead, and it's pretty, seems to me like black art to kind of coercive way to write.
So efficient implementation, I think, will take another 5 to 6 years.
So we can expect that witness or kind of witness functions will show up during runtime.
Well,
or is it solved? I don't know.
I don't know either. So I think that make it efficiently will take even more time. Right. Of course, it's simple example. So well, I don't know actually. So it will take some time.
I will say that sort of thing is what brings Idris to its knees. Like if you try to concatenate two lists and you don't explicitly state what each type one is, you're not doing anything for the next minute or two, because it has to figure out, hold on, runtime. Put this into the REPL, hit enter, walk away.
Yeah, but it doesn't have to be that way.
No, it doesn't. But I'm saying that the state
So
of the state of the art right now is.
In fact, well, we can come up with some better ideas actually. So what we can do with dependent types right now during compilation, maybe in a year or two we can come up with new ideas.
But are people hoping that the compiler will figure this out automatically, or do we expect that we annotate it and kind of superate or something? That
well, of course we'd like to have it automatically. Well,
we hope this. Is there hope for that, or do we?
I hope for that. But well, we know that.
The direction that people currently think is the true way.
I think from technical point of view, it's better to provide some annotations on that. So it will be easier to implement. But we don't want that. So it's not because the main line of research is to make it less annotated. So less annotated code is better for publishing papers.
Okay, but would it be a bad thing from practical point of view to have to annotate?
I don't know. I don't know. It's a difficult question for me.
There change one thing in your program and all of a sudden nothing is erased anymore.
Right. It's right. Yeah. Or you can quickly make your type checking like exponential time slower. It's also possible here.
We can do this already now with
Right. So it's quite difficult. All right. So here, let's look at this this function. Can you see two lambdas here? Have two different lambdas. Can you see it? there is one lambda with minus. This will be erasable lambdas for erasable variables, and another lambda without minus. It will be for non-erasable components here. And we have two alternatives, like two lines in this zip function. So the first line will be as follows for nil. So you can see here, you can find here proofs of impossibility of several options. So if you have nil for first argument and nil for second, then this is a proof that everything is all right here. And here is a proof that this is impossible case. So small proof system in there. So we see that it is impossible to have these two because they contradict to each other. And for another alternative, you will have proof here. One is not nil and another is nil. And this is another line. So it's quite. It should take a time to read this. So you can look at this paper and try to analyze it. But still, we have the same things as before. We have type level applications. Still, we have with square brackets. We have normal application here. And this is the same code without annotated types. So system D without explicitly typed. So it's the same. So if you look for enough time for these two slides, you will see that they are the same with type information there and without type information here in system D. And syntax for this new system D is very difficult. You can see these two kinds of lambdas for erasable and non-erasable components. You have coercions, you have some other stuff. I will not follow this anymore. There are many rules for evaluation, for typing rules. Almost all of these pictures, they were generated from Coq source. So you don't have to type them in LaTeX anymore. LaTeX, you just generate them. So you can write papers with lots of such fractions, and everything was generated. Right. Yeah, but yeah.
You read the Coq source.
Yeah, in fact, that's the. But first, you have to write this Coq source.
Does that mean that PhD papers are now a compile target?
Yeah, that's a good joke. All right. There are other components in this paper. So now progress and preservation, they are proved in Coq. So there are many rules for definitional equality, any other things. And this system DC, it has many properties. Unfortunately, see for this last line here. So as described in the paper, it does not have this. It does not feature this backward compatibility to system FC, because several parts of system FC lacks here, and that means that you will have to make full backward compatible implementation in order to inject it into GHC, and that will take a long time. Yes, question.
Which paper is this?
It's specification for dependently
Weyrich
typed
paper.
Haskell.
Stephanie Weyrich? Yeah.
Oh.
Thanks.
Yeah.
Alright,
Okay, and that's it. That's the last slide. And in these slides, I have many references. So I was talking about results presented in these papers. I'm not a researcher technically. I just read all those papers, understand them, and tried to deliver them in this three parts workshop. So there are many papers there, many papers and many papers. So I've read them for you to present them right now. It was rather difficult, I should say. Well, thank you very much for participating. Thank you very much for your questions. Thank you.
Can you take another question?
Yeah, sure.
Okay. Would make dependent Haskell certain language construct we have right now in the fronted Haskell redundant, like, for example, type families? You could just
Right. Yeah, you will have to throw them away. Yeah.
Great, actually, because
Yeah.
you just like the extra syntax all the time.
Right. unfortunately, I think we should have functional dependencies still in the language. Yes. Unfortunately, functional it's something that nobody understands correctly, and it's impossible to throw them away. It was one of the most difficult questions for writing next Haskell report, actually, because you cannot throw them away, and there are so many dark corners of functional dependencies. So even in dependent Haskell, you still will use them. You will have to use them. Yeah, another question. Yeah.
Did you use Beamer to make these slides?
Yeah, sure.
How hard is that to install on a Macintosh?
I don't know.
Okay.
Well, I use TechLeaf for that. So TechLeaf, I think there is distribution in Mac.
Thanks. You answered the question. You did. Yeah. Thanks.
Right. Okay.
Yeah, you had a question?
Yeah, sure.
So, I'm actually sort of like thinking about how this ties in with type level literals. So on one hand, you'd think they'd be erased by the time it hits core, but at the same time, that dictionary is being stashed somewhere, right? So I guess I'm kind of just curious, like the mechanism to it, where it like knows how to take like a type level literal, keep it, and then when you need to get it back, pull it out. It seems like it'll also somewhat tie into like these quasi-dependent type things, constructs.
Well, I think it's it's a difficult question. I think.
Taking a non-erased value type mat or kind mat, that is both the type level literal and value interspect.
So there is a library in Haskell, singletons, and they use these. So they have these types, and they have values which corresponds to those types. And you can erase types, but then still you have these values in your code.
Yeah, so it's kind of just like auto-generating like the instances or something like that.
Right.
More or less, yeah.
Right. So that
And then you can just toss them around in the core.
Right. So if you have dependent Haskell, then you don't need that anymore.
Right.
So you will have values at the same time.
Makes sense.
Right. I think so. Moving to dependent Haskell can throw away lots of things from Haskell. But
We only keep the term language essentially.
right. Maybe we will. It will be times when. So there is a big problem actually when you learn this Haskell for dozens of years, and you have to forget about half of a Haskell. Then it's a little bit. I don't like it, I spent so much time to understand all those type families, GADTs and stuff like that, and I just throw it away. It's a pity. All right, any more questions?
Are they going to still have to have roles?
What? Yeah, I think so. Yeah, I think they should have them. They still have coercion there, right? Yeah, I'm not sure about roles actually. I don't remember. So they do have coercions, but I'm not sure about. Well, I think they should have it because actually this stuff is used very extensively in boxing and boxing things. So when you have values which are unboxed for performance or boxed things, I think you still use roles there. But I'm not sure. Yeah, I don't. Yeah.
Are there still GADTs probably? GADTs will still be around because probably you can. What we use them for nowadays is a lot of essentially lighter.
Well, maybe I can't speculate on that. I don't know. I think it will be possible to program without JDTs. I think so. I'm not sure. Well, I don't know. It's like, yeah. Sorry. Yeah, I think so. Yeah, that's. All right. So okay, let's finish with it. Okay, thank you again.